as I mentioned today, I will share with you some things that we have been working related to multi-trait and multi-environment genomic assisted prediction using the SKM library. I will explain what is the SKM library and some of the facilities that offer to many people that is not very good at programming and in statistics. Yeah? As the presentation, I divided the presentation in three parts. The first is an introduction to multi-trait and multi-environment analysis. The second one, I will talk about the SKM library. And in the third part, I will provide illustrative example for implementing multi-trait, multi-environment genomic assisted prediction models in this library under three methods: Bayesian methods, generalized linear models, and partial least squares. I will start with the introduction. First of all, it's important to point out that all the R code is available here. You can download the R code and the R data and the data that I will use for the example in such a way that you can reproduce the results, and also if you are interested in, you can use with your own data this code. Yeah. The introduction.
Oswald, real quick, would you be able to post that link in the chat or Q&A? Or in the chat, so others
sure.
can just click on it.
I will share now in the chat in such a way that everyone can have access to this material. Let me share.
Thank you.
Let me share this information. This is the link, the code and data. Yeah, maybe you can see now in the chat. Okay, I will start with the introduction. In the introduction, I will talk about the important, why is really important multi-trait analysis and multi-environment analysis in the context of genomic prediction. As you know, most of the research done for genomic selection has been aimed at developing univariate trait models and very little at developing multi-trait models. Yeah. Unitrait models are trained to predict the only one single trait. For example, this can be continuous, binary, categorical, or count. And while multi-trait models are trained to predict at least two traits simultaneously, that is the difference. And for this reason, in multi-trait models, we can take advantage of the correlation between traits. Yeah. Multi-trait models should be preferred since they allow to represent complex relationships between traits more efficiently, exploit not only the correlation between lines, but also the correlation between traits, are much more interpretable than a series of trait models, are more computationally efficient to train that multiple unitrait models individually. Also, improve index selection because they allow more precise estimates of random effects of lines and genetic correlation between traits. Additional multi-trait models can improve index selection because they increase the precision of genetic correlation parameter estimates between traits. And also there are evidence that multi-trait models improve the power of hypothesis testing because we improve the power of hypothesis testing regarding to unitrait model. This means that reduce type 1 and type 2 errors. For this reason, multi-trait models produce in general more accurate parameter estimates and better prediction than unitrait models. For example, this guy, Scholtes 2017, found empirical evidence multi-trait models improve parameter estimates, and many authors, including Carlos and Birkham, Gia and Janit and other authors, found that multi-trait models outperform unitrait models in terms of prediction accuracy. Yeah? However, also many authors say that when the correlation between traits is low, using multi-trait models is not really advantageous, since the lower the degree of relateness between the traits, the lower the benefits of multi-trait model. This means that when the correlation between traits is null, we can expect the same result as using unitrait models. Multi-trait models are also known as multivariate analysis in the statistical literature, and due to their clear advantages over unitrait models, they have been applied for solving a great diversity of problems in areas like environmental science, education, chemistry, telecommunications, psychology, medicine, communications, engineering, food science, and et cetera, et cetera. This means that multi-trait models are very popular, not only in genomic selection, but also in other areas. The use of multi-trait models is not is not as popular as the use of unitary models due to the following reasons. There is less software available for performing multitrait analysis. This means that is a restriction for using multitrait analysis in the context of genomic prediction. Fitting multitrait models is computationally intensive and much more demanding than fitting unitrait models. Multitrait models are complex as traits and variables have different response patterns in different environments and therefore create very complex genotype by environment interaction. For this reason, fitting multitrait models in general is more complicated and requires more computational resources. Yeah. Multitrait models are based on a more this means that multitrait models require more assumption. For this reason, they are more difficult to train and to achieve. Yeah. Also, multitrait models increase the problem of convergence when they are fitted with classical methods like maximum likelihood or restricted maximum likelihood and more others. For this reason, in general, there are few software for performing multitrait models regarding to unitrait models. Analyzing multitrait models in the context of genomic selection is very challenging due to the size and complexity of the underlying data sets, which nowadays is common in many breeding programs. For this reason, multitrait models require more computational effort than unitrait models. Yeah. In general, multitrait models are of paramount importance since it allows breeders to select individuals that excel in multiple traits simultaneously, leading to more efficient and effective breeding programs. For this reason, by combining multitrait and multi-environment analysis, genomic selections can provide breeders with a more comprehensive and accurate prediction of an individual performance potential. It helps identify genotypes that exhibit superior performance across a range of traits and environments, leading to the development of improved varieties or breeds. Yeah. Additionally, multitraits enables breeders to select for specific trait combinations or optimize breeding strategies for different target environments, ultimately accelerating the rate of genetic age and enhancing the efficiency of breeding programs. However, due to the fact that genomic selection is a predictive methodology, still the implementation of multitrait, multi-environment genomic assisted prediction in many breeding programs is challenging. For the reason, some research is being conducted to facilitate the implementation of multitrait, multi-environment models to improve the accuracy of the genomic selection methodology. However, to be able to successfully use the multitrait models are of paramount importance, the statistical machine learning methods, because the genomic selection, as we know, is a predictive methodology. However, due to the lack of time and not enough training, it is difficult for breeders and scientists of related fields to learn all the fundamentals of prediction algorithms. Fortunately, with the smart or highly automated software, it is possible for these professionals to appropriately implement any state-of-the-art statistical machine learning method. For this reason, now I will explain a little bit about the SKM library and the facilities that offer for breeders to use to implement multitrait and multi-environment models. If there are any questions, please let me know.
You can put any of the questions. I think I enabled the chat, so you should be able to put it in there or in the Q&A. If that is not available, let me know in the Q&A because I am getting those messages. Yeah. So.
Okay. But I can see that you shared to all the people the link, no?
Yep, I believe so.
Okay, thank you. Okay, I will talk a little bit about the SKM library and the things that offer to implement multi-trait, multi-environment prediction models. Yeah. The name of the SKM means sparse kernel methods library. Yeah. The sparse kernel methods library is a library in R that allows to implement 7 of the most powerful state-of-the-art algorithms. We can implement Bayesian methods, random forest, support vector machine, generalized linear models, gradient boosting machine, partial least squares, and feed-forward artificial neural networks. For these 7 algorithms, you can implement unitrait models. but only for 4 of the 7 algorithms you can implement multi-trait models. Multi-trait models can be implemented for Bayesian methods, random forest, generalized linear models, and partial least squares. And today I will share to you how to implement 3 of these 4 multi-trait models. I will provide examples for Bayesian methods, generalized linear models, and partial least squares. The SKM library not implement the algorithm itself, but internally use some already popular libraries for this purpose, which are known to have efficient and complete implementation of the algorithms. SKM use the same format for implementing 6 out of the 7 state-of-the-art statistical machine learning algorithms. This means that in general, for implementing the 7 algorithms, the format is quite similar, which facilitates his implementation. For algorithms with hyperparameters, SKM has an easy way to specify the condition for hyperparameter tuning, which is really important because hyperparameter tuning is key for getting good prediction accuracy. Also, the SKM library has many easy-to-use functions for computing matrices for the evaluation of the prediction accuracy, which I will explain more later. Additionally, the library provides many functions for implementing many cross-validation strategies and for making summaries of prediction accuracy. In general, the way how the library perform the hyperparameter tuning is in this way. For example, the data, you first divide the data in testing and training, and internally the library divided the training in inner training and validation, and with the inner training, you evaluate many models, and with the validation, you select the best candidate model. After you select the best candidate model, internally the library refit the model using the whole training data, joining the inner training and validation, and with this repeated model, you perform the prediction for the testing set. Yeah. This means that in general, the library works in this way, split the data set in inner training, validation, and testing, but you only split the data in training and in training and testing, and internally the library split the data in inner training and validation. Then with the inner training and validation is selected the optimal hyperparameters, and then with this optimal hyperparameters is refitted the model with the whole training set, and finally these refitted models you evaluate the prediction accuracy in the testing set. Yeah. It's important to point out if you are interested in using the library, you need to copy this code, and in this way, using this code, you will be able to install the library. Yeah? And the key for installation of the library is to install these 4 lines of code. This means that we need to install these 4 lines of code, and there are some slight difference between different computers, but in general, using this code, you should be able to install, but first you need to install the dev tools. If you are unable to install the dev tools with the last code, you can download the dev tools and install manually. Yeah? You can download from this line that is in red. Yeah? Okay. Another important thing is that in SKM, we can implement also kernel methods. As you know, kernel methods are really efficient for capturing nonlinear patterns in the data, and the library allows you to implement 7 kernels. You can implement linear kernels, polynomial kernels, sigmoid kernels, Gaussian kernels, exponential kernels, and arc cosines with 1, 2, and 3, and 4 degrees. This means that these 7 kernel methods can be implemented almost in a very simple way, yeah, without so much line of codes. Yeah. Additionally, there are many metrics that there are many functions for computing prediction accuracy in regression problems and classification problems. For example, this function MSE, you can compute the mean square error for regression problems. For computing the root mean square error, you can use this function for regression problems also. And for regression problems, you can compute also the normalized root mean square error, the mean absolute error, the mean arcotangent absolute percentage error. And also, if you wanted to compute all of these matrix for regression problems, you can use the numeric summary and you can compute all of these matrices simultaneously. And for classification problems, you can compute the accuracy using this function, precision, recall, sensitivity, specificity, Brier score, and the F1 score, the kappa coefficient, the matrix coefficient, the ROC area under the curve using this function, precision, recall, area under the curve. And if you wanted to compute all of these classification matrix for computing prediction accuracy, you can use the categorical summary, automatically compute all the matrix for classification problem. Yeah. Also, for the context of genomic prediction, we can use the GS summaries. This is a specific function for the context of genomic prediction that expects a data frame with 5 columns. The first column can be the fold number. The second column can be line, the genotype. The third column can be the environment, and observe and predict. This means that you need to provide a data frame with 5 columns without, it's not important the order of the 5 columns, but with this data frame, the GS summaries automatically detect which type of response variable you are predicting and compute the matrix appropriate for regression problems or for categorical problems, but provides you the summary across environment, and for each specific environment, the summary. Yeah? This function returns 3 different summaries, compute the summaries by line, by environment, and by fold. I will explain you with example which is the output that produces the GS summary, but it's really nice because you, in an automatic fashion, you can compute all the matrices for categorical or regression problems without so much effort. Yeah? As I mentioned, for example, to use this GS summary, you need to provide a data frame that contains 5 columns. That the 5 columns, one is the fold number, the other is the environment, the line, and observed and predicted. And in this way, you can obtain summaries by line, by environment, and by fold. Also, in the SKM library, there are many options for types of cross-validation. For example, you can compute k-fold cross-validation. You can create the partition for k-fold cross-validation using this function. You can compute the stratified cross-validation, the folds with this function. For random partition, you use this function. And for random stratified partition, you can use this function. And for list 1 group out, that can be like list 1 environment out, you can use this function. For random line, you can use this function. And if you wanted to do real prediction in which you put as NA all the values that you wanted to predict, you can use CVNA and automatically use as training all the data that has phenotypic values. And for those that are missing values, you do the prediction. Yeah. Also, it's important to point out that because most of the statistical machine learning requires tuning, you can implement 2 types of tuning here. You can tune the hyperparameters using grid search and Bayesian optimization, and you need to specify the tune type. There are 2 options, grid search and Bayesian optimization. And also it's important that you need to specify the number of folds for tuning the hyperparameters. By default, you can use k-fold cross-validation and random. And you need to specify the number of partition or folds. Yeah? This is really important because at the end, the success of implementing statistical machine learning methods is to do a good tuning process. Yeah? For example, for implementing generalized linear models, you can use this function, generalized linear model. You need to provide the X training, the Y training, and also you need to put here which hyperparameter you wanted to tune. Here I am providing a grid of values for the alpha to be able to implement the elastic net. And if I put a grid of values, by default, you will use the grid search type of type of tuning. Yeah. But if you put, for example, a list with minimum and maximum values for each of the hyperparameters, you can use the Bayesian optimization, which is another way for hyperparameter tuning that in general is more efficient than grid search, because grid search, the quality of the prediction depends on how large and exhaustive is the grid that you provide. Yeah? And Also, at the end, you can extract the best hyperparameter combination, the best hyperparameters combination with this function. Now, I will go to the illustrative examples to be able that you can understand a little better how to use this function. And I will provide example for implementing multi-trait models only. As I mentioned before, I will provide examples for multi-trait and multi-environment genomic assistance prediction for Bayesian models, for generalized linear models, and partial least squares models. I will start with the Bayesian models. In SQM, we refer to Bayesian models to all those models that are in the BGLR library. This means that here in the SQM library, we will call the BGLR function for implementing the multi-traits and unitrait models. The implementation of the models unitrait or multi-trait can be done using the Bayesian model function. With this function, we can implement the Bayesian model in SQM. And in this case, the input consists of a list of components. For example, I need to provide a list with a predictor that contains a term for environment, a term for lines, and a term for genotype and environment interaction. And also, if I wanted to add environmental information, I can add another term. I will explain this thing with more detail in such a way that you can understand. Also, for implementing Bayesian models in the SQM library, for the training, the training and testing set, you will use a data set of the same size of the original data set, but you need to put NAs for the testing set for the response variable. For example, assume that I wanna to train a model with this predictor in which I have intercept terms, the effect of environments, the effect of line, and the effect of genotype by environment interaction, where the genotype, this is the distribution of the random effect of lines, where G is the genomic relationship matrix computed as Barrales suggested. This is the variance covariance matrix of trait that should be estimated from data. And this is the distribution of the genotype by environment interaction. And you can see here that sigma T2 is the variance covariance matrix for traits that also should be estimated. And here the genomic relationship matrix is provided for the user. And this is the distribution of the error. In this case, you can see that I have three terms, three components: environments, lines, and genotype by environment interaction. And for being able to implement this model, you need to create a list. In this case, the first list corresponds to the effect of environment. The second list corresponds to the effect of lines or genotypes, and the third is for the genotype by environment interaction. Then you can use the Bayesian model function. You need to provide the list and the response variable that is a matrix. And in that way, also you can provide the testing indices in which are the position for which are for which you internally the library will put NAs. And then you need to provide the number of iterations and the burning and the thinning. And in that way, you can implement the Bayesian models using this library. I will start now with some examples. As I mentioned before, the R code is available at this link. In this link are 5 examples for implementing Bayesian models for multi-trait prediction. I will start with the first example. For the reason I will move to the R code. If you cannot see my R code, let me know, please. Let me go to the R code. I will explain now a little bit this code. For example, in the first column, you can see the environment. In the second column is the line, and also in the third column is the same information, the line information, but I put hybrid name. In the fourth column is the first trait, grain yield, and in the last column also is another trait that is called height, plant height. And this is the toy data set that I am using. You have this data set. And you can see my R code. I return to the R code. Oh, I need to stop sharing.
Yep.
Yeah, okay. Okay, next, because it's important to point out that here in this R code, I have to I have two files. Yeah? I have three files. One is Pheno that contain the phenotypic information. That is other is Geno that contain the genomic relationship matrix. The next one is markers that contain the marker information. I will show you the markers. This is the marker information. It's called as 0, 1, and 2. Yeah. Okay. Then here I need to order the phenotypic data. I order first by environment, then by line. Then I order I will order in the same way the marker data. I extract here the IDs of the markers and genome. And here I am doing the ordering of the markers. I am saving markers here. I am putting the dimension of marker. The dimension of marker is 2,264 markers. I am putting in the same order as the phenotypic data. Yeah. Then I am doing the scaling here of the, I am standardizing each of the columns of the markers. Then to be able to simplify the computation, I will not use directly the markers. I will use only, I apply the singular value decomposition to reduce the dimensionality of the markers. And then in this case, I will compute, I am computing in this line the genomic, the design matrix of lines. Yeah, this is the phenotypic data. I am computing the design matrix of lines. Then I compute, I integrate the markers to the design matrix of lines. I am incorporating here. Then here I am computing the design matrix of environments. I am deleting one column to avoid redundancy. Then here I am computing the genotype by environment interaction, the interaction of the environments with the genotype data. And then I create the list to be able to implement the model. In this case, the list contains three terms. The first is the effect of environments, and I put fixed because I am assuming a flat prior. And here I am putting the effect of the information of lines, and this is the information of genotype by environment interaction. And I will put variation risk regression. This means that I will assume for each marker and for each marker by environment interaction, a normal distribution with mean 0 and variance sigma squared. And for the first one is also mean 0, but with the variance 10,000 or a larger value. Then I select which should be my response variable. My response variable, in this case, I have two traits. I wanted to predict the two traits simultaneously. I select the Y. Then I use this function, cross-validation CV random line. With this, I will perform 5 false, and in each fold, I will assume that 20% of the information of the lines is missed. I will predict 20% of the lines, and I will use the 80% of the line for training. This means I will create 5 partitions, and in each partition, there are 80% of the information for training and 20% of the information for testing. You can print this one to be able that you can show a list in which there are all the you can see here. You can see here the first fold. These are the position for testing. These are the position for training. For the second fold, the same thing. These are the position for testing. This is a position for training. For the third fold, the same in the same fashion. And there are 5 partitions. You can see this is for 5 partitions. This is the position of testing. This is a position for training. Okay, and then I will create a list for saving the predictions. I create a list with 2 data frames. the list one for the first trace and the second for the second trade to be able that I can save the predictions for each of the trades. Then here I do a for loop for each of the faults. I select the first fault. Then I put N8 for the testing positions for each fault, and I say here the testing. These are the response variable for the testing, and you can see here this is a kind of matrix because Y contains 2 columns. And then I will use the variation function, the variation model function, and I will specify eta. Remember, eta is a predictor, is a list. In this case, this is the list that contains 3 terms, one for environment, the other for lines, and the other for genotype by environment interaction. And here, I provide the eta, I provide the Ys, the response variable, but with NAs for the testing positions, and I will do the prediction for those positions. Then I will train only with 100 iteration, but sure, you don't need to do that. You need to put 10,000 or 20,000 or 30,000, but only to be able that I can run quickly here. And finally, I extract the predicted values. Using predict, I extract the predicted values, but the predicted values are extracted for the position of the testing for those that I am interested in doing the prediction for which I have missing values. Then I save the predictions because the predictions contain a list of 2 traits. I save the prediction for grain gene, and here I put in the fault number, the line, the environment, the observed and predicted, and here I am saving the lines that belong to the first fault, second fault, and so on. For this reason, I am doing rbind to be able to concatenate all this information. But the key thing here is that I am creating a data frame that contains 5 columns. One is for fault, the second for line, the third for environment, the fourth for observed values, and the last one for predicted values. And also I am doing the same for the other trade, for the hate trade, but contain the same information, only the predicted values correspond for this trade now, and contain fault, line, environment, observed, predicted. And finally, I can run this code and I can get the prediction performance. I will run the code. I will select and run the code, and you can see that it's quite fast because I am using only 100 iterations. And you can see that I performed five partitions, and you can see that it's done. Yeah.
Oswald, just one quick question. People are asking, could you those 4 lines where you install from GitHub the SKM library? Can you paste that in the chat as well? Some people are having trouble downloading the SKM package.
Oh, okay, yeah. I will provide the code in such a way that you can try to install. Yeah.
Okay.
I will copy the code and I will share to you. Okay. Let me to finish this example. For example, here, as I mentioned, the training process is done for the 5 partitions. The training process is done for the 5 partitions, and I will return to let me return to here because it's done the predictions. Now I can use the GS summaries with the GS summaries for the first trade. Yeah? And I will run this one, and everything is okay. Now I run the first one, and now I will print this information that I just run, and you will see the prediction accuracy. You can see here. Now I obtained the summary of the predictions for each environment, for environment 1, 2, 3, and across the environment. And I computed the mean square error, the standard error, the mean square error, the root mean square error, the standard error, the mean square error, the normalized root mean square error, the standard error, the normalized square, the correlation and his standard error, and so on. All these matrices, all the matrices for regression problems were computed for each environment and across environment. This is the job that that the GS summaries can do that. And also, as I mentioned before, the GS summaries allows you to detect what kind of response variable you are working on. If the response variable is categorical, compute matrix for categorical summaries. If the response variable is continuous, compute matrix for continuous response variable. In this case, because the predictions are continuous and the problem is predicting continuous response variables, the GS summaries provide all the matrix for continuous response variable. Okay. Also, I save here. I save the results. I save in Excel. Then here I will do the GS summaries, but also for the other trade. Yeah. Now for the second trade.
Are you on the right screen, or is your R frozen, or? So it looks like you're still
you can zoom my R code or not?
You can see your R code, but can you move your mouse? I think your screen might be frozen.
I don't know. I will share again. I hope this can be fixed.
Okay, there you go.
Okay. Okay, now I will compute the matrix for the second trade. And you can see here, these are the matrices for the hate trade. And also you can show exactly the same format for the prediction accuracy. For each environment, you can compute the prediction accuracy for this environment is called Cintalapa, Coitas, Equipilas, and across environment. And you can compute all the available matrices for computing prediction accuracy in the context of multi-trade and for continuous response variable. And as I mentioned before, the GS summaries detect what kind of response variable you are predicting. If the predictions are categorical, you will compute matrices for classification. And if the predictions are continuous, will be computed matrices for continuous response variable. Okay. Okay. Now I hope you can reproduce these results. I will share to you the R code to be able that you can install the library. I will pay in the chat. This is the first part. I will put you the second part.
Okay. I think, yeah, we posted it to everyone. I think you maybe had just posted it to the host and panelists, but everyone should have that code in the chat now.
Yeah, also, if someone has difficulties because sometimes for computer there are problems, you can send me an email and I can help you to install and in such a way that you can use without any problem. Okay. Okay, I will continue with another example. Mm-hmm.
Thank you.
I will continue. For example, here in this data, as you mentioned, is a multi-environment data because I have more than one environment, and it's a multi-trade because I have two trades. Yeah, and for the reason in the predictor, I included three components. Yeah? Three components. This was for environments. This was for lines or genotypes, and this one for the genotype by environment interaction. But here, because it's a Bayesian model, I am not using the GBLAB. I am using the Bayesian regression, yeah, for these two terms. Yeah. Also, now I will explain you another example for implementing the GBLAB model in the context of multi-trade prediction. Let me go to open the second file. Okay, this second one is the same as you mentioned, as you can see here. You can see the R code. Hello?
Yes, yes.
Okay, as you can see, it's the same data set that contains three files. One is the markers, the other is the phenotypic data, and the other is the genomic relationship matrix. Here I am doing the ordering first for environment, and then each environment, the lines are sorted, are ordered. And here I am computing I am extracting, I am ordering the markers. Here I compute the design matrix. The only thing here is that now the training process was done without genotype by environment interaction. I put only 2 terms in the predictor. All the rest of the code is exactly the same, But now I will train the model taking into account in the predictor the effect of environment and the effect of genotypes without genotype by environment interaction. But the code for the training process is the same. I don't modify anything. Everything is the same. Here I am computing the false. I am computing 5 false, but you can change here the proportion of testing or training. I have put here 20%, you can put 30%, it's up to you. Yeah? I put 30%, and I create a list. The list, as I mentioned, should be, if you wanted to predict 5 traits, the list should have 4 data frames internally. Yeah? But because here I am intending to predict only 2 traits, the list contains 2 data frames internally. Yeah? And also the remaining part of the code is the same, but here also in this part, if you wanted to predict 5 traits, this means that you need to use a block of code like this one for the first trait, a second block of code like this one for the second trait, and you can add a third block of code for the third trait, for the fourth trait, and for the last 5 trait. Okay, this means that is the logic of using the code, and in that way you can use without any problem. Now the model should be trained only taking into account two terms in the predictor. This means environments and genotype, and the code is exactly the same. And I will run the code, and you will saw that it's quite fast because I am using only 100 iteration, and you can show here the summary of prediction accuracy in terms of mean square error, normalized root mean square error, root mean square error, mapped, and correlation coefficient. And it saved the prediction accuracy. Okay. For sure that if you use more iteration, will require considerable more time, the training process. Okay, now I will move to another example, but for implementing the GBLAT model. Also in this case, as you can see here, was implemented for Bayesian risk regression. Okay. Okay, I am using this. Can you see my R code?
Yes.
Okay, as you can see here, it's the same data set. It's exactly the same data set. It's the same data set that contains environment, line, hybrid name that is equivalent to line and to trait. Yeah? This is the format of the data that you need to provide to be able that you can use without any problem, the library. Then I am ordering the data, but now the computation of the input is different because I will use the GBLAT model. Now I compute here exactly the same, the design matrix of lines, but now I will compute a kind of linear kernel for including the genomic relationship matrix. Now here I am ordering the genomic relationship matrix according to the phenotypic data, and here I am creating the linear kernel for the lines. Also, I will put GBLAT for the 3 terms. I am creating a kind of linear kernel for the environmental information. Yeah? Exactly in the same way, but here I am assuming, because I don't have environmental information, I am assuming that the environments are independent. For the reason I am multiplying by the cell without anything in the middle. Yeah? But if you have a kind of environmental relationship matrix you can include in this part of the, in the middle of this computation. And here I am computing the genotype by environment interaction, the product of the two kernels, because are of the same size. You can do this without any problem. And then this means that now you have a linear kernel for genotype by environment interaction, you have a kind of linear kernel for environment, and you have a kind of linear kernel for lines, okay? And then you create the predictor. Also is a list with 3 terms, and I will apply GBLAT, Bayesian GBLAT for each of the components. And also this is the matrix of the response variable. There are 2 traits. It's a matrix of 2 columns. And here I am computing the random partition also with the same number of faults and the proportion of testing the same. But also, as I mentioned in the library, there are many options for computing other cross-validation strategy. You can use civil random, you can use stratify, etc., etc. But I am using this one because it's quite popular here in genomic prediction. Then I creating I creating a list for saving the predictions. And here, this list, this list contains 2 data frames, one for each trait, but if there are 4 traits, you need to create a data frame with a list with 4 data frames. Yeah. And also in the same way here, you will start the loop for each of the falls. You select the first fall, and then you put NAs in the response variables. Then you use the Bayesian model. You provide the eta, the response variable, the number of iterations, and here I will put less to be able that I can run quickly. And here, and then you obtain the predicted values for the 2 traits, and then here you save the predicted values for the first trait, and creating including in this data frame fall number, line, environment, observed and predicted. And then you do the same thing for the second trait. You create the first column for fall, line, environment, observed and predicted. And you are putting here the observed values for the second trait and the predicted values for the second trait. And in that way, you save all the predicted values, and you are taking into account that belong to this fault, to this line, and to this environment. And in that way, you can use the GS summaries. And with this GS summary, you can compute the prediction, the summary of prediction accuracy for each of the traits. Yeah? This is for grain yield, and this is for hay. Yeah? And I will run this code until here, and you will saw that it's quite straightforward. This implementation for sure with few iterations. Yeah? And you can see here that you get the summary for grain yield under this GBLAT model. And you can see here is the prediction accuracy for the first environment, for the second environment, for the third environment, and across environment. And also here the correlation for the first environment, second environment, third environment, and across environment, okay? And at the end, you can decide which matrix you will report for your report, for your study, okay? And also, finally, I can compute the prediction accuracy, the prediction summary for the last trait. For the last trait, I will use this one, GS summaries, and this is for the second trait. And also you get the prediction summary for this trait, and you can see here that this is the mean square error for each of traits and across traits. And also here I am saving the prediction accuracy with right CSV. With right CSV, I am saving the prediction accuracy. And you can see that it's quite straightforward. The only thing that is different here with regard to Bayesian regression is that here I put Bayesian GBLAT for the 3 terms. And for implementing the Bayesian GBLAT here, you need a kind of linear kernel in this case. And the linear kernel of environment is computed in this way. You compute first the design matrix of environment. You then do this cross product of the design matrix of environments, and you divide by the number of columns, and you compute the linear kernel for environments. And in this way, you compute the kernel, the linear kernel for the expanded linear kernel for genotype, and also doing the Hadamard product, you obtain the genotype by environment interaction kernel. Okay. And also, if you wanted to add more terms, you can put comma here, and you can start adding more terms in the predictor, and in that way you can implement a multi-trait, multi-environment model with additional information. Any questions so far? Okay. Now I will open the for code, and the for code is the same, but only without interaction term. This is the for code without interaction. You can see that everything is the same. The only difference here is that only now I am not including the genotype by environment interaction. I am putting only 2 terms in the predictor. The first term is for environment, and the second term is for the lines of genotypes. And the remaining part of the code is exactly the same. Now I will run with 1000 because this is not so complicated. I select the whole code and I can run, and you can see that it's done the second iteration, the second fold, the third fold. Now it's done everything. Yeah. And this is the prediction accuracy. This is the summary. Okay. Next, I will go to the last example for Bayesian models to illustrate how you can implement a kind of kernel model, a kind of nonlinear kernel for computing for predicting multi-trait, multi-environment data. Let me to close this one, and I will open. In the 5 example, I will implement the Gaussian kernel. Yeah. Yeah. Can you see my R code? Okay. Hello?
Yes, Oswald.
Okay. Yeah, I can see that. You can hear me. For example, here is the R code, as I mentioned, is the same data, cheese toy data. First here, I am doing the ordering of the phenotypic information first by environment and then by line. Then I am doing the ordering of the markers in this part. Here I am scaling the markers. This means that I subtract the mean and I divide by the standard deviation. Then I can use this function for compute the kernels. Kernelize. I can use this function, and as input I will provide here in this case the markers. I'm providing the standardized markers, the standardized false, because I am standardized outside. And then I choose the kernel. As I mentioned, there are 7 types of kernels that you can choose. One is the linear kernel. The other is the Gaussian kernel. The other is the polynomial kernel. The other is the sigmoidal kernel. And the last one is the arc-cosine kernel. And with 4 options, with 1, 2, and 3, and 4, this is the degree of depth of the arc-cosine kernel. Yeah? And the proportion of rows should be used for computing. Here I put 1, but if you wanted to put sparse kernels, you can put a value less than 1. Yeah? And here I will standardize a kind of standardization. I will divide by the number of columns the markers. Then to be able that I have almost around 1 in the diagonals, I do this. I divide the computed kernel by the mean of the diagonal elements, and in this way I compute the Gaussian kernel. And you can see here, the kernel is of dimension 300 by 300. It's exactly the same dimension that for the genomic relationship matrix. Let me check here. For example, you can put in the genome, the dimension of the genome. Here I string 100 because I remove the 1 column to identify the lines, but it's 300 by 300. Yeah. But because this is ordered, I don't put the identifier of the lines of genotype. Now I have the kernel, the Gaussian kernel, because I put here Gaussian. Next, what I did is to compute the design matrix of lines in the same fashion. This is the design matrix of line. Then I compute this is the Gaussian kernel. I put Gaussian kernel because here I am using the computed kernel, the Gaussian kernel. This means that it's the implementation of the kernels in the Bayesian model is quite similar to the GBLAB, only replacing the linear kernel by another type of kernel. That's it. Yeah? And in this case, I am using here the Gaussian kernel in place of the linear kernel computed with the markers. And then here I compute the design matrix for environments, and here I am computing the linear kernel for environments. And then I am computing the genotype by environment interaction, doing the product of the two kernels of the environment and lines. And finally, the implementation for the Gaussian kernel is quite straightforward. Also here I create a list Bayesian GBLAB for each of the components, and the remaining of the code is exactly the same. You don't need to change anything to be able to use this model without any problem. Okay, I will run the whole code. I think I didn't change the number of iterations. Yeah, I will stop because we need more time. I will put 100 only to be able that I can do quickly. Okay, now it's running, and you can saw that in this way, using this function, using this kernelized function, you can compute many kernels, different kernels, and implement in the GBLAB, in the GBLAB model without any problem. Yeah. Okay. And this is the output. This is the prediction accuracy with this Gaussian kernel. Yeah. This is the prediction accuracy.
Oswald, we have one question in the chat. Is it possible to include the experimental design in this type of model?
Yeah, yeah. It's important to point out that here I am. Yeah, this you can implement in a one state. Yeah, you can implement in a one state, taking into account the predictor, the experimental designs and works, or also you can do in a two state, but you need to be careful with the weighting part. Yeah.
Yeah, also, we have just one more. How do we overcome limitations to handling large matrices in R, especially in this type of?
For example, if you wanted to include the experimental design, this means that you need to add in the predictor the components related to the experimental design to do in a one state process. Yeah? This means that, for example, if you have block effects, you need to add one part for the blocks and another part for the blocks nested in location or something like that. This means that you can use the library for implementing in one state, taking into account the experimental design. Yeah? Without any problem, but we need to be careful in the creation of the design matrix, because the design matrix should be for each of the components also in the experimental design. Yeah? Mm-hmm. Okay, let me. I will stop sharing this one, and I will move to the slides again. I hope you can see the slides. No, I need to share again. You can see you can see my slides, Jan?
Yes.
Okay. Okay. Now I will point out some things related to Bayesian models before starting for the other models. Kind of conclusion. Bayesian methods are powerful for predictions since they incorporate prior information. The prior could reflect uncertainty about parameters that is actually fixed, or the variety of values that a truly stochastic parameter could take. Yeah. Also, Bayesian methods are robust methods that without a complex tuning process produce competitive predictions. Also, these methods allow to specify some model assumptions. For example, you can implement for unitrain models bias A, bias B, bias C, Bayesian lasso, and for multitrain, you only can implement now Bayesian risk regression and GBLAP, and check model quality and sensitivity to these assumptions in a straightforward way. Also, it's important to point out that Bayesian methods belong to linear models, but also they work with kernels, and in this way, they are able to capture nonlinear patterns in the data when they are present, and in that way, you can improve the prediction accuracy because linear models are not so efficient for capturing nonlinear patterns. One advantage of Bayesian methods is there are not convergence problems like other, but the problem is that there are not convergent problems, but it's more demanding in terms of computational resources compared to conventional mixed models. Yeah. Bayesian methods require a bit more mathematical formalism, but with friendly software, they can be implemented by many users of different backgrounds. Yeah. Now, I will move to generalized linear models. It's important to point out that generalized linear models in this library is using the GLMNet library as backend, yeah. But we can use in SQM with a simple way for his implementation. For example, in this case, for generalized linear models, the distribution of the response variables can be some of the exponential families like normal, binomial, and Poisson. This means that for generalized linear models, you can implement response variables with normal responses, binomial, and Poisson, and the predictor is only in this way. Yeah? You can include only, there are no different components for each of the sources of information. That is a limitation. And the link function depends on the types of response variable. For example, the link function for normal responses is identity. For binomial is the logistic or logic, and for the Poisson, the exponential link function. Yeah? And internally, as I mentioned before, we are using the GLMNet library, and the cost function or loss function that minimize this library is this one, in which we can see that this is the negative of the log likelihood plus the penalization. And when alpha is equal to 0, we can implement the risk penalization or risk regression. And when alpha is equal to 1, we can implement the lasso penalization of risk or lasso regression. And when alpha is between 0 and 1, we can implement the elastic net penalization. Yeah? And as I mentioned, for continuous response variable is using the identity link function. For binary or binomial, we are using the logic link function, and for categorical, use the generalized logic link function, and for counts, use the exponential logic function using the Poisson model behind in the likelihood, in the log likelihood, negative log likelihood, sorry. Under the SQM library for continuous response variable, it is possible to train multi-train models. Also, only for continuous response variables in the SQM library, it's possible to implement multi-train models. And the function for implementing the generalized linear models in SQM is generalized linear model. The required parameters for this function are shown in the following code. For example, this is a function for implementing generalized linear models. Generalized linear models, you can put the X training and the Y training. And here, if you put alpha equal 1, you will implement lasso regression. If you put alpha equal to 0, you implement the risk regression. And if you put alpha between 0 and 1, you implement the elastic net regression. And also, if you put a grid of value for alpha, you can use the grid search or the Bayesian optimization. And here you need to specify the number of faults for doing the tuning process. And if you implement Bayesian optimization, you need to specify the number of samples to start the process and the number of iterations under Bayesian optimization. Yeah. Also, by default, the generalized linear models use 100 values of lambda as in grid search, and it selected the optimal value. Yeah. Next, I will move to some examples using the GLM, the generalized linear models in the SQM library. I will provide 4 examples. I will provide 5 examples, and as I mentioned before, all the R code is available in this link. I will move to the R code to be able to show you how to implement these models. Let me to share again the code.
Oswald, while you're doing that, we had a question on how to deal with large matrices using SKM. Wondering if you could expand on that.
What do you say?
I was wondering if you could address a question on using large matrices in the SKM package, how to deal with large file size or large matrix sizes.
Sorry, I don't understand very well. Can you repeat again? I cannot hear well.
Yeah, so the question is actually in the chat and in the Q&A addressed to the host and panelists. Did you see it? If that helps.
Let me check the. Okay, yeah. Regarding to the, regarding to when the data set is quite large, it's not so efficient the Bayesian models, because the matrices are so huge and still they are not optimized in this library. Yeah, but for this reason. In this context of big data, it still is not quite good, the library. Let me to go to the example for GLM with Bayesian optimization. Can you see my code?
Yes.
For example, here, the data set is the same. The data set is the same. Also, the phenotypic data, first I order the phenotypic data, then I order the markers, I create the design matrix. And also here to the design matrix of genotypes, I incorporated the marker information. And then here this is the design matrix of environment. And this is the design matrix of genotype by environment interaction. And now here, because this is a generalized linear models, I cannot specify for each component. I cannot specify in one. I need to specify all the information in only one component. For this reason, I put cbind to concatenate the information of environment, genotype, and genotype by environment interaction. And here is the same information for computing the false. And for implementing this one now, the function, the slide, the thing that is different here is one, is that in X, I concatenate information of environment, genotype, and genotype by environment interaction. That is really important to point out. The second important thing here is that I divide the data set in training and testing. For example, here I divide for each fold the X training and X testing, the Y training and X testing. Here I am selecting the information of training. Here I am selecting the information of testing. Here I am selecting the information of false. And here I am selecting the information of testing for the Ys. Yeah, these are for the Ys for the response variable, and these are for the inputs for the inputs for the model. Then for implementing the generalized linear model, I use X training and Y training. And then here, because I will use Bayesian optimization for choosing the optimal alpha, I need to put a list with the minimum value of alpha and the maximum value of alpha. As I mentioned before, if alpha is equal to 0, I will implement the risk regression. If alpha is equal to 1, and implement the lasso regression. And when alpha is between 0 and 1, it's called the elastic net regression. But for Bayesian optimization, I need to provide a range of the through the space of this response variable. And here I will use Bayesian optimization. I will use 5 samples as a starting for computing the for the evaluation, and I will use 10 iterations, but you need to put more iterations if you want. And by default, use 100 values of lambda. And then after the training is done, I compute the prediction for the testing set. Yeah. This is the prediction for the testing. It's important to point out that here I train the model only with the training information. I not put NAs for the testing set. Yeah. Then I do the predictions, and I do the prediction. I extract the prediction here. I extract the prediction here for the grain yield with this way. And here I am extracting the prediction. I am extracting the true values for the grain yield, and also I am doing the same things here for the. I am extracting the observed value for height, and here I am extracting the prediction for the predicted values for height. Yeah. And here is the summary. The prediction accuracy is exactly in the same fashion. And here is the summary for environment. And I am saving the information, and I can run, and that is it. As you can see that in general, as I mentioned, the format for saving the information is quite similar. It's quite is almost the same with the slight differences. And for the reason, it's more easy to implement the models only using one library than trying to implement the models with the different libraries that are behind the SKM library. And you can see here that now is doing the tuning process. As I mentioned before, I provide the X testing, X training, Y training, X training, and internally the library divide the training information in inner training and validation for doing the Bayesian optimization for selecting the optimal hyperparameter. And after the optimal hyperparameter is selected, is refitted the model using the whole training information. And with that refitted model, finally I performed the prediction for the testing set. Yeah? And for sure, the larger the number of iterations that you put for computing the optimal hyperparameters, the more time will require for training. Yeah? But for sure, if the more iterations or you put for the selection of the hyperparameters, it is possible that you can guarantee a better tuning process, or you can guarantee a better selection of the optimal hyperparameter. And here is now, you can see that now just finished the first fold after using Bayesian optimization. Now just started the second fold using the Bayesian optimization, and in this way will perform works the library. Okay, we'll take some minutes. Okay, but I will make emphasis in this part. The computation of the design matrix is exactly the same as before as in the Bayesian risk regression. Yeah? But now for providing as input, I need to create this matrix in which I put together the information of environment, genotype, and genotype by environment interaction, okay? And the other thing that is different here is that I need to divide in each fold. I need to provide the X training and the Y training, yeah? And with the X testing, I will provide the X testing for making the prediction. Here I am providing the X testing for making the prediction. Okay. And the Y testing are my true values. And with this, I will compare for computing the prediction accuracy. Yeah? Y testing. Okay. Let me solve if this is done. It still is running. Yeah. Okay. Also, to be able that we can, I will open the other code with Bayesian optimization, and the code is the same. The code is the same, but now it's with no interaction. Only I remove from the predictor the information of environment. This is the only difference. This means that now the training should be done only taking into account the predicted information of environment and information of the genotypes, okay? And all the remaining things are exactly the same, Mhm. Okay, it's still running. Yeah, it's taking some time. Now it's done. The second fold is in the third fold. For a while, I will explain you the other two codes that I have here. The third code is, this is with grid search. Okay. It's important to make emphasis that the input is the same. This is the input. Okay, but now I will use for the training process the grid search strategy. This means that for the tuning process, I will put many values as candidates alpha in this case, because I wanted to tune the alpha hyperparameter. I will put 5 values of candidates alpha, and internally the library by the training in inner training and validation, and is evaluated the performance with each of these alphas, and then is performed 5 folds, compute the average of the validation accuracy in each of the for each of the parameters, and at the end is selected the alpha that provides the lower mean square error in terms of prediction accuracy, and with this optimal alpha is refitted the model, and with this refitted model are done the final prediction. This means that now in place of using the Bayesian optimization, I will use the grid search. Yeah? And this is the difference. The other things are almost the same. Also for doing the prediction, I use this one. I put the predicted model. I put the trained model here, and the X testing, I do the prediction, and I am saving here the prediction in the same format, the fall, line, environment, observed and predicted, and in that way I can use the GS summaries for computing the prediction accuracy. Okay, let me check that if the result is done. Now it's done the 1, 2, 3, 4, only 4. It's not finished yet. Next, I will open the fourth code. The fourth code is for with no interaction. It's the same as before. But only now, not taking into account the genotype by environment interaction. You can see here it's not included the genotype by environment interaction, but also is with grid search. Grid search, and I am putting the candidate values for the alpha hyperparameters. And as I mentioned before, the larger the candidate values, is more possible that we can get a better tuning process. Yeah? Okay, let me check how many. Okay, as you can see here, the problem of using Bayesian optimization and the tuning process is quite time consuming, and for the reason is not so efficient from the point of view of time. Yeah? But the problem is that if you wanted to get optimal result, it's always recommended to do a tuning process. But if you wanted to do without tuning, only you need to specify here. If you wanted to use lasso, you need to put 1 here. If you wanted to implement risk regression, you need to put 0 here. And in that way, the running process should be really fast, because you are not doing any tuning process. Okay. Okay, let me to move to the last example. For example, this is the last example. I mentioned this last example. I will stop this one because it's taking so much time. 1, 2, 3, 4. It's almost done. Okay. I think it's almost done here for the 5. And here is the summary of the prediction accuracy. Okay. I see something in red here. Yeah, it's for the same, not a problem. And this is the accuracy using the generalized linear model for implementing the multi-trait model for continuous response variables. As I mentioned before, in the SKM library, using the generalized linear model, only we can implement multi-trait model for continuous response variable. And this is the last one, the last. For example, as I mentioned before, if you are not interested in performing a tuning process that you want to implement the lasso, you only need to put one, and it's quite fast in this way because it's not taking long time. Yeah. Let me run this one, and you will saw that it's quite quickly. It's done the first false. It's on the second fold. And as I mentioned, if you wanted to implement the risk regression, you only need to put here 0. Right? If you wanted to implement elastic net regression, you can put, for example, 0.5 or another value between 0 and 1. Yeah? But the point is that without tuning these parameters, not always is optimal. Yeah? And these are the results. And here say that cannot be computed efficiently the correlation because there are not variance in the data, but that is not a problem. And this is the prediction accuracy in terms of mean square error. Okay. Okay. Now I will stop sharing. I will move to the sorry, let me to move to the slides. Let me to share again. Finally, I will say some things about the generalized linear models. In general, generalized linear models are a powerful framework for implementing genomic selection models for continuous binary categorical and count response variables. But still in the SKM library, only we can implement multi-trait models for continuous response variables. But for unit-trait models, as I mentioned, we can implement models for continuous responses, for binary responses, for categorical responses, or for count response variable. And in the cases of continuous responses, it's assumed the normal distribution. For binary responses, it's assumed it's a binomial distribution using the logic, the logic limit function. For the categorical, also is implemented under the multinomial distribution. And for count response variables is used implemented under the Poisson distribution. But for multi-trait models, only can be implemented for continuous, for normal distribution. As I mentioned before, in the SKM library for generalized linear models, we can implement lasso regression, risk regression, and elastic net regression. The implementation of GLMs is quite efficient in terms of time of implementation if you are not using the tuning process, but with the tuning process require considerable more time. GLMs are unable to capture nonlinear patterns in the data. For the reason you need to be aware of about this limitation. The tuning process is quite efficient for models that have few hyperparameters. In this case, we need to tune 2 hyperparameters, the alpha hyperparameters, but for sure, if you put a large grids or a lot of iterations, the time will be considerable. Next, I will move to the last model for implementing multi-trait models, and this is partial least squares. Partial least square regression is one of the most popular in biological science because it can model complex biological events. It is flexible for considering different factors and is unaffected by collinearity. Yeah? For this reason, some authors suggest that PLS is a potential, it's a really important model for working in high dimensional biological data. And for this reason, it's quite popular in biological science for dealing with genomics, proteomics, and peptidomics data. Yeah. PLS can model multiple responses while efficiently dealing with multicollinearity. Yeah. And next, I will provide 2 examples for implementing PLS for multi-trace models. I will provide one example taking into account the environment plus the genotypes, and only one example for not taking into account the genotype by environment interaction. Let me go to the examples. Let me go to the example. Let me to share again the. Can you see my R code?
Yes.
Okay, let me to go to open the example. Okay, the data is the same. The data is exactly the same. The input required for implementing PLS is exactly the same as the generalized linear model. We need to provide in only one matrix the information of environment, genotype and genotype by environment interaction. And the other things are exactly the same, but now the difference is this. In place of using generalized linear models, we will use partial least squares. And this information also is provided for the training and for the testing. That is really important. Yeah? And here you put the X training, Y training, and then you can do the predictions with the trained, with the adjusted model. You put the X testing and you can obtain the prediction for the testing set. And the saving process is exactly the same. It's exactly the same as before. And using the GS summaries is almost the same. It's exactly identical. For the reason I will not lose time explaining these things. The only thing that we need to be aware is that the input should be given in only one matrix, concatenate information of environment, genotype, and genotype by environment interaction. And also that you need to provide X training, X testing, Y training, and Y testing, and should be trained the model with the trained information. And then you can compute the predicted values, providing the information of the inputs of the testing, and in that way you can extract the prediction values, and finally you can save the predictions and compute the matrix for this one. Let me run this one. Also, this partial least squares, when the data set is very large, it's not so efficient computationally. That is another problem that has. Now it's running the first fold. It's running the first fold, and will take some minutes maybe. Okay, let me to open the other file. Now it's done the first fold. It's starting the second fold. One important thing here in PLS is that the only is required to tune the number of components to maintain. Yeah? But this is done internally for the reason we don't need to worry about tuning with the partial least square. Yeah? But the point is that for large data set, it's not really efficient from the computational point of view. Okay. Finally, the last code that I wanted to show you for partial least squares is related to the same example, but without taking into account the genotype by environment interaction. This means that in X, in the information of the input, we will not include, for example, we cannot include this one. I will delete this one, for example. This means that in this case, we are not taking into account the genotype by environment interaction. Okay. Now it's in the second fold. It will take some minutes, but it's not so bad the time required for multivariate partial least squares. because as I mentioned before, is only one hyperparameter is required to be tuned. That is the number of principal components to retain. That is also done with cross validation. Okay, finally, I will return to because it's not finishing yet. It's in 1, 2, 3, 4, 5. It's only one more fold to finish. Okay, let me to go to the slides. Okay, I will say some things about partial least squares. Partial least squares. Partial least square regression is somewhat close to principal component regression. Like principal component regression, partial least square regression involves projecting the response onto uncorrelated components. That is a linear combination of predictors. Unlike principal component regression, the way partial least squares compute the principal components is different, the way how they are computed, but the most important thing is that in the computation of the principal component is taken into account the response variable, which is not taken into account in the partial principal component regression. Yeah? We can conveniently express the solution in terms of the original predictor. This means that at the end, we can obtain the predictions in the original response, and also we can compute the beta coefficient in the original response, even though that we train the model with the latent variable. Yeah? Partial least square regression is not based on any optimization criteria, rather it's based on it's an interactive algorithm that we always converge. In general, the algorithm for PLS is quite simple. Yeah, you don't need to invert any matrix. You don't need to diagonalize any matrix. All you need to do is compute simple regressions. This means that the computation of the parameters in partial least squares is not so complex. Also, partial least squares work for multivariate responses, but here in the library only for multivariate continuous responses. Yeah? Also, it's quite efficient for dealing with more predictors than observations, and for sure that is very efficient for correlated input. Yeah. And finally, I wanted to make some things that are important, and I think there are many areas of opportunities in multi-trait and multi-environment modeling. For example, one area of opportunity is to develop more efficient models from the computational point of view, because in general, the models are not efficient, large data set and take long time. Yeah. For this reason, there are a lot of opportunity for developing more efficient models in terms of computational point of view. Yeah. Also, there are areas of opportunity to develop more efficient models to capture better the correlation between environments and traits. Yeah. Some models capture the correlation between traits, between lines, but not capture the correlation between environments. And I think there are opportunities for improving the current models. Also, there are opportunities to develop multi-trait models for mixed response variables. This means that the model can allow you to train a model with binary response variable, with continuous response variable, for categorical response variables, and count response variable. Because nowadays the current models are only for continuous, only for binary, only for categorical, and only for counts. But in the context of genomic selection, only for continuous response variable, we have quite efficient model. Yeah. And for sure that there are a lot of areas of opportunity for developing models for larger data sets, for big data. And finally, I wanted to say some final comments. Multi-trait models are progressively using a pivotal position within the realm of data analysis for plant analysis, animal genomic assisted breeding, due to the continuous and rapid advances in computational power, and for the substantial advantages offered by multi-trait models in refining parameter estimates and enhancing prediction accuracy. This means that the acceptance of multi-trait models is basically because they are more efficient from the computational point of view, and because they estimate with more precision the parameters, and also because they increase the prediction accuracy. For this reason, multi-trait models are key to the timely identification and meticulous selection of the most advantageous candidate genotypes in plant breeding. Yeah. Also, multi-trait models provide advantages over single-trait modeling because, as I mentioned, improve prediction accuracy and because allows to incorporate correlated traces, and also, as I mentioned, can be really useful for index selection because the parameter in this case can be more efficiently estimated. In scenarios where the aim is to predict intricate or economically burdensome traits that exhibit a correlation with less costly secondary traits, the incorporation of multi-trait models can prove instrumental in formulating improved strategy for genomic selection. Similarly, improvement of the accuracy of prediction for low heritable key traits can follow from the use of high heritable secondary traits. Furthermore,
are you trying to share your screen right now?
what?
Are you sharing a screen right now, or are you?
You cannot see the screen?
No.
Let me go through.
Okay.
You can see the screen now?
Yes, we can see the screen now.
Okay. Also, as I mentioned before, another final comment is that in general, multi-trait models can be efficiently used for improving the prediction accuracy and the parameter estimates in plant breeding for improving the selection process. Yeah? While the advantage of the multi-trait model is clearly documented, large data sets and more computing resources are required, as there are additional parameters that need to be estimated. For this reason, still, even though there are many options for implementing multi-trait models, they are not quite efficient because there are the need for implementing these models in big data sets. Yeah? Additionally, in multi-trait models, there are convergent problems that often arise and make the implementation more difficult. Even though that in the Bayesian context, these problems are not common, that doesn't happen, but they require considerable time for implementation. Yeah. And finally, as conclusion, I wanted to say that the SKM library provides an opportunity to utilize various statistical machine learning techniques for multi-trait, multi-environment genomic prediction without the need for extensive expertise in statistics and programming. As you saw in the example, it's quite straightforward, the implementation of any of the statistical machine learning methods for genomic prediction in the SKM library, because many tools are automated for you. In that way, it's more easy the implementation. Additionally, in SKM, the user can incorporate other types of omic data, such as genomic, phenomics, and other omics information, which has been shown to enhance prediction accuracy based on empirical evidence. For this reason, the goal of this library is to democratize the implementation of genomic prediction. But however, still there is need for more easy to use software, and that can be automated and open source. However, still is challenging the implementation of multi-trait environment genomic assistance prediction in the context of many traits, large inputs, and small sample size. Yeah? For the reason, more research, more efforts, and resources are required to solve these current problems for implementing multi-trait and multi-environment predictions models in the context of genomic selection. And that's it from my part. I don't know if there are some questions.
Thank you, Oswald. We did have one question. I don't know if you tell me would have answered this already, but what is a tuning parameter and how tuning parameters contribute in the predictive model?
Yeah. Okay, but most of the statistical machine learning models require some parameters that are not learned from the data. And for this reason, before using the final model, you need to specify these parameters. And at the end, we choose this parameter using kind of cross-validation. For this reason, we divide the training data in inner training and validation to be able to select which is the optimal combination of hyperparameters that can guarantee reasonable prediction. For example, in the case of the model of generalized linear models for continuous response variable, there are only two hyperparameters. One is the lambda, the degree of regularization, and the other is alpha, if the model can be strictly risk regression with alpha equal to 0, or strictly lasso regression with alpha equal to 1. But if you want something in the middle that can produce good prediction, you need to select these hyperparameters in a reasonable way. But for doing this one, you need to you have the necessity to split the data, the training data in inner training and validation to select this combination of hyperparameters that can guarantee better prediction. But for sure, this requires more computational resources. And for this reason, most of the time, the people prefer some models that don't require a complex parameter tuning.
Does anyone else have any other questions in the chat?
Yeah, also there are another questions that say that in general, when there are many lines, cultivars, and many environments, it's complicated to implement this model. Sure, it's very complicated because we need a lot of computational resources and sometimes it's not enough. But for the reason I mentioned the areas of opportunity for implementing this model is that we need to continue doing research and for being able to implement this model in a more efficient way. Yeah. And the other question, as you asked before, is possible to include experimental design in the model? Sure, you can include the experimental designs in the modeling process in the SKM library, but you need to be careful to take into account each component of the experimental design in the predictor to guarantee the appropriate prediction or the right prediction. Okay, the other question is the slides. I will put the slides in the same link to be able that you can have access to the slides.
Yeah, Oswald, if you put that on the link, and then if you send me the link and then any of that code, I'll also, for like for downloading the package, I'll put that in your GitHub link on the description of this recording on YouTube. Which
also there are one more question that's if we can perform hybrid prediction using the SKM library. Sure, if you want one example, I can share some example for hybrid prediction also in the SKM library without any problem. Okay, the other question say, what do you think about comparing these methods with deep learning approach? Yeah. Okay. In general, we have done this kind of comparison, but for implementing deep learning models you require more computational resources, and also you need to gain significant experience for implementation to be able to get reasonable predictions. But still, the implementation of multi-thread deep learning models is quite complex, not so easy. But in some cases, you can outperform the conventional mixed models or conventional Bayesian models, but with a lot of work. You need to work a lot to be able to get the reasonable deep learning model. But the good thing is that continue growing the availability of more open source that facilitate implementation, and I think very soon this can be done more easily.